I think it's fair to describe PsiQuantum as sitting on the extreme end of the spectrum of quantum computing companies, in that from the very beginning, we've just been singularly, pig-headedly interested in building the very large-scale, universal, fault-tolerant, million qubit scale machines that, honestly, the whole industry has always known would be required for genuinely commercially useful applications. And the approach that we use to build that is we use single photons, so particles of light. We made the first demonstration of 2-qubit gates by our CEO, Jeremy, 20+ years ago in Brisbane using those photons. And now we put those on a chip, repurposing the silicon photonics technology that was originally developed for data center applications, and which I was really excited to hear you speaking about in the keynote. We think that gives us profound advantages in overcoming the scaling challenges that face our field: manufacturability, cooling power, connectivity, and control electronics. And that leverage has put us in this position where we're now breaking ground in the next few months on very large-scale data center-like quantum computers in Australia and in Chicago.
The last audience was already talking about usefulness of their computers in running industrial software. On the other hand, there's some common sense about the number of qubits necessary to have a productive and functional system. And we're at 36 or X number of qubits at the moment, and now you're talking about 1 million qubits for a fault-tolerant machine and a productive machine. And so how do you bridge that gap from where we currently are, what's the current state of the art, versus where do you think we reach a plateau, not a plateau, but a phase shift? It's likely not likely to be a very specific point, but the usefulness of these quantum computers will become more and more and more useful over time. When do you kind of see that transition happening?
More than one of us on this stage has got themselves in trouble by making comments on timelines, of course, and found ourselves in difficult positions and so on. But I really appreciated the other piece of your quote, which went missing, which was that we got to scale up by 100,000x, by 5 orders of magnitude. And I think in our field, of course, that is really hard. And in our field, unfortunately, I think there is a lot of wishful thinking from people desperately, and I understand, I'm sympathetic, desperately hoping that we can make the machine useful before it's useful. But you have to scale up by about 100,000x, and it's natural to say that that's a multi-decade exercise for human beings. Feels that way in the dead of night. But you of course, have extraordinary demonstrations that it doesn't have to be a multi-decade exercise. XAI, Colossus, they built a 100,000 GPU cluster, famously, in 112 days. How did they do that? What miracle did they deploy to get that done? The answer is the $1 trillion in 50 years that has gone into the semiconductor industry. And I came back a couple days ago from Global Foundries. I've been raging about the insane leverage that we can access there for 8 years without ever having actually stepped inside the fab. And I was extremely lucky to get in there a couple days ago. And it's a religious experience because you see just how insane the capability of the fabs, the contract manufacturers, the OSATs, and so on is. And that has always been our thesis. And to your question on when, there are basic questions that you should ask. And this is a very complex field. Everyone is arguing for their particular technology. I'm no different. But there's a whole separate set of questions, in addition to fidelity and so on, which is, can you tell me who your fab is? Can you tell me who your OSAT is? Can you tell me who's doing contract manufacturing? And where is the site where you're building the machine? And these are necessary but not sufficient conditions to actually being ready to build a genuinely useful machine. And it's very hard, but that is what we've really sort of spent our resources towards. And I think it's very exciting that you now see other players in the field taking steps into that same kind of regime.
Yeah, in fact, Pete, as you were talking, all of the things that you're mentioning are very sympathetic with us, because Recently, as you know, we introduced this idea called silicon photonics co-packaged optics, and the semiconductor physics had to be invented. The packaging technology, how you stack it, how you manufacture it, the entire supply chain. I introduced a whole bunch of new supply chain manufacturers. We were able to, of course, leverage many existing industries. If not for that, and we had to invent everything from the ground up, it would have been impossible for us to do that. And so in a lot of ways, you guys are doing what we did with silicon photonics CPO, at a multi-scale challenge. And so Pete, what are we going to talk about next year?
Yeah, so I mean, now we're making thousands of wafers of quantum chips in global foundries at a pretty high level of maturity. We're building large cryostats with no chandelier. We're stringing together heaps of optical fiber. And I really hope that you'll have us back next year. Next year, I think I'll have to wipe the mud off of my boots before I come up on stage here, because as I said, we're breaking ground on these two very large sites, so like 500,000 square foot kind of sites in Australia and Chicago.
Pete, you look like a builder from Australia.
Well, I'm trying my best, but yeah, thanks very much for having us.
All right, guys, thank you. Thank you.